Okay, so today's lecture is on molecular geometry, and there's actually three what I would call objectives for this lecture. The first one is to understand how the absence or the presence of lone pairs of electrons affects the geometry of a molecule. And then we need to know what the various geometries are and how to predict them. Tomorrow in class you'll be doing that, or for you guys, tomorrow in class you'll actually be doing that. You'll be working with these model sets up here in groups of 4, and you'll have a very specific assignment to do. Draw Lewis structures, then use the Lewis structures to predict geometries, and then make the model, and then show me the model, and then I'll check it off. Okay? And then you'll turn in a group sort of lab sheet. So we do have a lab tomorrow. However, it is basically a non-chemical lab. It's a model lab. Okay? So that means you can wear your shorts. Okay? Understand the concept of orbital hybridization, how it changes the bonding in atoms such as carbon. And that will be on Friday. Resonance and hybridization. We'll finish off with that. Okay? So, without any further ado, what is molecular geometry? In its simplest form, it's just the arrangement of atoms within a given molecule. The arrangement of atoms within a given molecule. One of the important things here is that if I draw a molecule, and I'm going to draw as simple as I can get, water. We already draw Lewis structures for water. We draw lone pairs. Turns out that they're usually in p orbitals, which look like this. When I say geometry of the atoms, I mean these 3 atoms. Okay? Those 3 atoms, not the lone pairs. Not the lone pairs. Okay? So we're going to learn that the lone pairs affect the geometry. However, they're not part of the geometry. Okay? So that's the first thing. Okay? And then what I just described is how do the electron pairs affect geometry. There's a theory called valence shell electron pair repulsion theory. Okay? VSEPR. Okay? VSEPR. So the arrangement of atoms within the given molecule and VSEPR. Okay? Okay? Now, if you go, you should before class tomorrow, you really should read section 8.3 of your textbook. It's really short, just 4 pages, and it sort of summarizes a lot of what I'm going to talk about today. It's sometimes good to get it in 2 places, okay? 2 places, section 8.3. So the first thing we're going to talk about is VSEPR theory, valence shell electron pair repulsion theory. And the first is that it makes an assumption, and it makes the assumption that electron pairs don't like each other, okay? They don't like each other. So electron pairs repulse each other, you know, kind of like the guy that always is bugging you and you're like, ooh, stay away from me. They repulse you. That's how electron pairs feel, okay? And it turns out that this has consequences, okay? It has consequences. The first one is that this repulsion causes the electron pairs to orientate as far from each other as possible, okay? As far from each other as possible. Okay? And when they do this, they start affecting the geometry of a molecule. And in a little bit, you'll see how just adding lone pairs will change something from being a straight line to being bent, okay? From having a crook in it, okay? Just by having electron pairs. And the other consequence is that atom centers want to be as far apart as possible. Okay? They want to be as far apart as possible. So those are sort of 2 consequences of valence shell theory. So the 2 things that we want to take into consideration. Okay. I have 2 sets of models here. Okay. Turns out today you're going to learn about 5 geometries. Unbelievable, I have 5 molecules. Okay. So I'm going to pass these around. One of the ones I want to point out to you is this one here. I'll give this to Ankit. It has this metal rod thing, which are the atoms, and then these two plastic pieces are supposed to represent the lone pairs. These are actually Dryden molecules, and they were actually very, very, very expensive at one time, and now they don't make them anymore because basically computer programs, molecular modeling have kind of rendered these obsolete because the computers can do this so much quicker, okay? And in 3 dimensions as well now, okay? So let's give you an example of this really quickly. Besides knowing what water is, okay, you should also know and memorize the formula for ammonia, NH3, okay? You should know these two, okay? Ammonia. Now, one of the things I want to point out is if ammonia could just be left alone, what it would like to do is, if I can find it, where's the molecules coming around here? Are they by you? I'm going to pick up this one. So if ammonia could, it would love to be like this, a flat plane. Why? Because after all, this is as far apart as the atoms on each end can be. Okay? This is as far apart as they can be. Anyone know what would the angle be between each of these two? 120 degrees. They would be the absolute farthest apart. 120, 120, 120. However, when you add this lone pair of electrons, you can already see how it's sort of pushing down on these 3 hydrogens. And so actually what ends up happening is, you end up getting this right here. This is an ammonia molecule. The lone pair is assumed to be up here. It actually pushes it down. The hydrogen atoms are actually closer. If you measured, you'd see they're closer now than in the previous structure. And this is actually called something called trigonal pyramidal. Kind of makes a pyramid, like a flattened pyramid. And so that's the consequence of having a lone pair of electrons, right there. It actually changes the geometry of this. Why is that important? Well, it turns out that geometry will tell you whether a reaction will occur or not. It's quite possible on the other one that was perfectly flat, reacting material could come in from the top or the bottom equally. But now this one, because it's more kind of congested on the bottom, it probably is the reaction is going to occur on the top. Okay? So these types of things have consequences in terms of trying to figure out something known as reaction mechanisms. Okay? So I'll pass these around. These are similar to the ones that I gave you, except for they're these Allen and Bacon models. These are the ones you'll work with tomorrow. Okay? 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 So, now again, remember what I said before. I said that if you actually look at these actually have the same shape. If you were to count the electrons, they're in the same orientation. It's called tetrahedral orientation. But when you remove the electrons, you can see they have different shapes. This one's called bent. This one's called trigonal pyramidal. Okay? These are the 2 shapes. Now, let's talk about the first one is linear. It's pretty straightforward. 2 atoms on either side. How can they be furthest apart? By being 180 degrees away from each other. Okay? 180 degrees. And they make 2 bonding pairs. Okay? Okay, 2 bonding pairs. So, that's linear. No lone pairs of electrons. Now, if we just go to this configuration bent, this is like water. Notice it's the same AX2, but now all of a sudden, because we have the 2 lone pairs pushing down, we get a pretty remarkable change in geometry. Someone said, last period asked, well, would our world be different? They literally asked this question, would our world be different if water was straight, like the previous one, and not like this? And the answer is, there would be no life anywhere in the universe. Absolutely. Because it turns out that water is a polar molecule. Because it goes like this, it has a negative side and a positive side. It actually does something called hydrogen bonding. And hydrogen bonding is like the way all of our DNA connect. It's the way lakes stay Water stays in lakes, so the Earth used to be completely frozen. Life was stable to survive at the bottom of lakes. Every year, everything would die in a lake if it wasn't for hydrogen bonding. And you'll learn as we go on, it's probably one of the most important physical concepts. The other thing that you guys aren't really aware of about water is that water is an actually pretty unique, weird substance. You don't see it because you just play with water every day. You know what water's like. But if you were to walk into our reagent thing back there, there's hundreds of liquids. If, say, water is one of the liquids, there's 99 other liquids. The 99 other liquids are similar to each other and have properties much different from water. So water is actually kind of a weird substance. Okay? So the next one is this one I showed you, the flat one, trigonal planar. Again, 120 degrees. These ligands are as far apart from each other as possible. Okay? They're as far apart from each other as possible.
I like how you spiced up these slides.
Thank you. Okay, next. So that's trigonal planar. So remember that word. Can you guys say it? Trigonal. Not trigonal. Trigonal. Means three. And planar means it's flat. So the next one is trigonal pyramidal. So all that's happened is we've added one lone pair.
So it turned into a pyramid.
And it turns into a pyramid, yes. And it looks like NH3 would be an example. Or PH3, phosphine. Okay? The lone pair.
Wouldn't anything 3 be? Wouldn't anything 3?
Well, there's only certain ones that form 3. Group 5. Okay? So, again, that's the difference between trigonal pyramidal and trigonal planar. Okay? And we have one more left. Okay? And the last one is actually kind of the king of the molecular geometries. And it's actually quite important. This one right here, tetrahedral. Okay? So tetrahedral, a perfect tetrahedron. Okay? Which element makes tetrahedral bonds? Anybody? Which element makes tetrahedral bonds? Carbon. Very good, Manolo. Carbon. You know, if you go to America, America is probably the biggest place where there's organic chemistry. They have a journal. It's called the Journal of Organic Chemistry. In Japan, which is probably the second, yeah, I know, right? Ooh, that makes sense. Journal of Organic Chemistry. In Japan, we had already taken the name Journal of Organic Chemistry, so they actually called their Journal of Organic Chemistry tetrahedron. Okay? In other words, this guy right here. Every angle is always 109.5 degrees. Okay? And it's always easy to remember because it's the only one that has a 4 here. All the other ones are different. So here's a summary. And I always have students come up to me and say, I have a tough time memorizing these. Memorize them in pairs. So here's the first two. These two right here. Okay? The only difference is pairs of electrons. Okay? So if you can remember AX2, but one has 2 lone pairs. Otherwise, they're the same. Okay? The next one, 2 pairs to remember are the trigonal. One doesn't have a lone pair, one has a lone pair. Okay? So remember those as a pair. And then you only have one left. And that's one that's kind of on its own. It's tetrahedral. These 3 geometries, people, these 3 geometries, if you were to look and count the electrons, the lone pairs of electrons, they would all look tetrahedral as well. Okay? So notice, yeah. Oh, I'm sorry, actually just these 2, X3 and X2. Okay? So they're sort of subsets. Okay, you giving up on taking notes, Matt? Okay. So note A represents the central atom and X represents the attached atom. And that'll be it, I think. Class over? Wow, it's amazing how that happens.